Dear ladies and gentlemen, my name is Katarina Holla. I am from University of Žilina, and I am going to present presentation, risk assessment and treatment in accidents prevention. Every manufacturing enterprise, service company or transporter wants to be successful. Their goal is to increase prosperity through production or services. Industrial risks are very closely linked with the technological processes and equipment, which have become the subject of assessment and solution, as well as permanent monitoring from the side of the companies and selected bodies of the state administration. Ignoring and paying insufficient attention to the risks could bring negative consequences for all participating parties. Technological progress brings mankind face to face with sophisticated and dangerous technologies, which can be a source of dangerous situations or industrial accidents. The tragic disaster of Chernobyl, Seveso, Flixborough, Bhopal, and many others prove the failure or incorrect usage of technological processes or their elements. Although the probability of the rise of these events was very low, their real consequences were huge. The manufacturing enterprises working with risk technologies have to deal with systematic and complex risk management. Its part is the risk assessment, which this presentation is dealing with. The preparedness of companies for the prevention of industrial disasters in the European Union as well as abroad cannot be achieved without a high level of expertise in the people making decisions and the analysts assessing the risks. At present, there are several possible approaches to risk assessment which differ not only from the point of view of the terminological terms of the individual phases, the sequences of steps, but also from the point of view of the content itself. In European Union, the catastrophic accident in the Italian town in Seveso in 1976 prompted the adoption of legislation on the prevention and control of industrial accidents. The so-called Seveso Directive was later amended in view of the lessons learned from later accidents such as Bhopal, Toulouse, or Enschede, resulting into Seveso II. In 2012, Seveso III was adopted, taking into account, amongst others, the changes in the Union legislation on the classification of chemicals and increased rights for citizens to access information and justice. The directive applies to more than 12,000 industrial establishments in the European Union where dangerous substances are used or stored in large quantities, mainly in the chemical and petrochemical industry, as well as in fuel, wholesale and storage sectors. Considering the very high rate of industrialization in the European Union, the Seveso Directive has contributed to achieving a low frequency of major accidents. The directive is widely considered as a benchmark for industrial accidents policy and has been a role model for legislation in many countries worldwide. The European Union has been solving the society-wide area of preventing the major industrial accidents which can threaten the environment and life, health and the property of the EU citizens through its center. It is Joint Research Center and Major Accidents Hazard Bureau. Major Accidents Hazard Bureau is operating two databases. The first one is EMARS and the second one is SPEARS. EMARS and its purpose of the EMARS is to facilitate exchange of lessons learned from accidents and near misses involving dangerous substances in order to improve chemical accidents prevention and mitigation of potential consequences. All major industrial accidents are thus recorded in the database EMARS. This major accidents reporting system was established to handle the information on major accidents submitted by member states of the European Union to the European Commission in accordance with the provision of the Seveso Directive. Actually, Mars holds data on more than 450 major accidents events. This figure 1 shows a 10-year overview according to the classification type of events that has happened in European Union and are recording an EMAR database. Based on the figure 1, 2, and 3, it is impossible to estimate the development of the rise of major industrial accidents in the next time period. The main reason is especially the fact that the rise of this kind of crisis phenomenon is not easy to foresee, especially because the basic cause of the rise of major industrial accident is the element that is very difficult to anticipate, and it is human factor. In spite of the maximal effort exerted for prevention, the major industrial accidents still occur. It is always necessary to take lessons learned from this accident. As to the system Mars, new lessons learned from recent industrial accidents in this database have been as follows. The first one is explosion in an ammunition dismantling facility. Then it is release of toxic substance mining activities. Then it's fire at a dry goods warehouse. Then is mobile vacuum tank explosion in petrochemical or oil refineries. And then is accidents in an oil refinery, petrochemical refineries. One of the major industrial accidents was the Bhopal disaster, also referred to as Bhopal gas tragedy, was a gas leak incident in India, which was considered the world's worst industrial disaster. It occurred on the night of 2 to 3 December in 1984 at the Union Carbide India Limited pesticide plant in Bhopal. Over 500,000 people were exposed to methyl isocyanate gas and other chemicals. The highly toxic substance made its way into and around the shanty towns located near the plant. Estimates vary on the death toll. The official immediate death toll was 2,259 people. The government of Madhya Pradesh confirmed a total 3,787 deaths related to the gas release. A government affidavit in 2006 stated that the leak caused 558,125 injuries, including 38,478 temporary partial injuries and approximately 3,900 severely and permanently disabling injuries. Another accident happened on 15th of March in 2012 in mining company in Finland. One worker died after breathing hydrogen sulfide while working in the yard. Worker had not used a gas meter or gas mask, and high concentration of hydrogen sulfide were detected in the area before and after the accident. The big problem was that the worker had not used a gas meter or a gas mask, and high concentrations of hydrogen sulfide were detected in the area before and after the accident. There was also established an accident investigation group and realized that the company has had environmental problems. During the investigation process, there were a huge interest from the media, and Turks had to prohibit the restarting of the process. One of the main tools to prevent these accidents happened in prevention phase is risk assessment and treatment. On this slide, you can see risk assessment divided into two phases, its preparatory phase and realization phase. Both of them are divided into several steps. There are several approaches to the risk management in the industrial environment. This process can be perceived as a part of the security and safety analysis, which is generally understood as studying the system, identifying the risk sources and dangerous situations in the whole system and their reduction and control. It is a formal title for understandable and systematic investigation of the engineering system, especially for the industrial processes, which can cause injuries of person, depreciate the property, or damage the environment if the stability is lost. Realizing the risk assessment requires the presence of at least two persons, the decision maker and the analyst. The following questions are to be answered in the phase of planning the analysis. The first one is, what do you want to know and why? The second one is, what assumptions are acceptable? The third one is, what is the time framework for realizing the risk assessment? And the last one is, who will join the process? The main objective of the risk assessment or analysis is to provide the decision maker with the information for a correct decision in an environment full of uncertainties. In cooperation with the analysts, they have to create clearly defined questions which the analysis and risk assessment are to answer. Sometimes it is difficult to characterize the person of the analyst who should assess and analyze the whole industrial process. Several character properties and professional qualities are introduced in the text, which continues. His or her person should fulfill these attributes. The first one is creative thinking, then reliability, deliberation, the ability to communicate, partial mathematical thinking, a team spirit, impartiality. The risk assessment is affected by several factors which determine the quality of its realization. Overpriced and lengthy analysis with a needlessly high number of participants can cause a negative final effect. There are several reasons for which a risk analysis can be wrong and insufficient. As I mentioned in the last slide, sometimes risk assessment and its results should go wrong. The results could be summarized into a few key areas when we can assume that the analysis will not fulfill the expectation of the decision maker and analyst. If it cannot give answers to all the key questions, if too many assumptions are in the analysis, and if not enough data or experts are not available for realizing the analysis. As it was mentioned before, one of the areas utilizing the security and safety engineering analysis is also the major industrial accidents prevention, which is managed by the Seveso Free Directive in the European Union. And the main tool in the prevention framework is this risk assessment. The basic aim is to prevent the rise of a major industrial accident and to assess the risks resulting from utilization of hazardous substances in environment and industrial processes. Every member country transposes the Directive Seveso Free in its legal environment, and in the Slovak Republic the most important guideline is Law number 128 from the year 2015, about prevention of major industrial accidents. Currently, in European Union, there are used several systematic approaches which the experts implement into the practice. Currently, there are several systematic approaches which the experts implement into practice. The first one is probability approach, PRA and PSA. Then is quantitative approach, QRA, CPQRA. Then is complex approach, MOSAR. Then is complex approach, Aramis. And QRA, a risk analysis software like FAST and Safety. In the framework of the aforementioned approaches, the individual steps make use of the principles of the following selected methods: fault tree analysis, event tree analysis, bow tie diagram, HAZOP, HAZAN, what-if analysis, Ishikawa diagram, FMEA, checklist analysis, and PHA analysis. Risk assessment of industrial processes using hazardous substances consists of several steps. First of all, it is necessary to choose those hazardous substances, what is really based on the cards with the security and safety data from the preparatory phase, which can be designated as selected or specified. The SHS are then compared with the existing list of the selected hazardous substances listed in Seveso III directive. If the selected hazardous substance, according to the corresponding legal regulation, exceeds the reference value introduced in the tables of the law about major industrial accidents prevention and shows a dangerous property, the company is categorized into the class A and B, what should be represented in European language as the upper tier and lower tier establishments. This phase consists of two steps which are depicted on the slide. The first one is the list of selected hazardous substances, and the second one is identifying dangerous devices. The identified SHS and devices are subsequently attached to critical events. The first one is decomposition, the second one is explosion, then it is materials set in motion, entertainment by air, then is materials set in motion, entertainment by liquid, start of fire, crack of casing in vapor phase, crack of casing in liquid phase, leak from liquid pipe, leak from gas pipe, catastrophic crack, vessel collapse, and roof collapse. Subsequently, based on the identified critical events in connection with SHS and devices, there were created the bow tie diagrams, which are a principal contribution in the area of the major industrial accidents prevention. The basic tree structure was taken over from the Aramis procedure, and the calculation rules were adapted to the currently used approaches. The selection for implementing barriers to the individual trees was left open, as it is depicted on this picture. The investigators themselves entered their name and names and characterizations, as well as the success level. On this picture, there is presented created bow tie within the software tool. Based on the created bow ties for the stated critical event, it is necessary to determine the probability or frequency of the causalities which are on the FTA side. the partial frequencies or probabilities of causes are written directly into the created software or into the created tree, and relations according to the Boolean algebra recalculated the frequencies with enter other nodes. Also, the probability or frequency and barriers in every branch are mutually in an interaction. In the end, the impacts of an accident are determined, which are based on the created bow ties which were mentioned before. Before we define them, it is necessary to simulate the development of the crisis phenomenon by appropriate software tool for us to find out the extent of the hit area. This should be done by software Aloha. Based on the simulation, we subsequently determine the impacts on life, property, and environment. The impact classification is based on the assessment of the effects on human targets and effects on the environment. In the end of risk assessment, it is really necessary to identify if the stated risk value is acceptable or not. In the European Union, we stated this value as the individual and social risk. Individual risk should be defined as annual risk of death of serious injury to which specific individuals are exposed. The social risk should be expressed as the relationship between the probability of a catastrophic incident expressed as the average frequency with which it can be expected to occur and its consequences. In risk assessment, results could differ from expectations. We call it uncertainty. Uncertainty should be divided into three groups: the parametric uncertainty, the model uncertainty, the overall uncertainty. The parametric uncertainty results from the variability of the input data for the same event and exponents. The model uncertainty can be considered the assignment of uncertainty to a suitable structure or mathematical form of the model. The overall uncertainty is a special category of the model uncertainty connected with phenomena determining the method the model was created by. What should we conclude for risk assessment and industrial accidents prevention? The risk assessment of the technological processes in the industrial environment, the subject of this educational presentation in this area, which is highly actual nowadays, both from the point of view of the scientific knowledge and the social practice. The technological processes having at disposal hazardous substances are potential threats for the employees, people around, and public, environment, and property. Therefore, it is inevitable to pay increased attention to their prevention. Thank you very much for your attention, and I hope you enjoyed it.